Welcome back students to another video lesson from the topic of waves. In the previous video lesson we have studied about formation of standing waves in a string fixed at both the ends. Now today we shall proceed our discussion on standing waves. Now this time we will be considering the formation of standing waves in a pipe closed at one end and discuss the different modes of vibration. So as you can see right now on the screen, we shall consider a pipe open at the left end and closed at the right end. Let us regard the right end, that is the closed end of the pipe, as the origin, that is x equal to 0. Then a wave pulse which is moving from its left end to the right end along the x-axis. A wave pulse that is moving from the left end to the right end along the x-axis, that shall be given by this equation, y dash equal to r sine 2 pi by lambda vt plus x. Now when this direct wave pulse meets the rigid boundary at the right end, it is reflected back. It will be reflected back. And now the reflected wave shall be given by y double dash equal to minus r sine 2 pi by lambda vt minus x. So now on superposition of this and this wave, on superposition of the two wave pulses, we can get the displacement of the resultant wave by using the superposition principle, which is y equal to y dash plus y double dash. Let us substitute the expressions for y dash and y double dash. So therefore we get y equal to r sine 2 pi by lambda vt plus x minus r sine 2 pi by lambda vt minus x. So on solving, we get the resultant displacement y as 2r sine 2 pi by lambda x cos 2 pi by lambda vt. The amplitude of the stationary wave formed in this case is given by 2r sine 2 pi by lambda x, which varies with the distance x from the origin. Now we have considered the pipe to be closed at the right end, that is x is equal to 0, and it is open at x equal to L. L is the length of the pipe, so it is open at the left end and it is closed at the right end. So in the open end we shall be having an anti-node, that is the position for maximum displacement, and in the closed end we shall be having a node. A node will be formed at the closed end. So in this manner we can get the boundary conditions. So y is equal to 0, that is for node at x equal to 0, and y is maximum at x equal to L. So for amplitude to be maximum, obviously the argument for sine, this has to be considered, and this should achieve a maximum value. So sine 2 pi L by lambda is equal to plus minus 1. An antinode is formed at x equal to L. So sine 2 pi L by lambda is equal to plus minus 1. So we know that sine 2 pi L by lambda, and this one value will be achieved for this condition when it is 2n minus 1 times pi by 2, and n can have values 1, 2, 3 and so on. So in this manner, on further solving, we get L to be equal to 2n minus 1 times lambda by 4. This shall be the general expression for the position for formation of an anti-node, and in using this particular expression we can discuss the different modes of vibration. So let's begin with the first mode of vibration, that is for n equal to 1. Corresponding to n equal to 1, this equation is going to give the first mode of vibration in case of a pipe closed at one end and open at the other. So if lambda 1 is wavelength of the standing waves set up corresponding to n equal to 1, then we get L equal to lambda 1 by 4. We simply substitute n equal to 1 in this expression, and this will give us L equal to lambda 1 by 4. Or we may write down lambda 1 to be equal to 4L. So obviously in the first mode of vibration, L is equal to lambda 1 by 4. That is, the length of the pipe will be equal to 1/4 of the wavelength of the waves. So in this manner, the wave will be formed, as you can see in this diagram. So if nu1 is the frequency of the wave setup, then we may write down nu1 to be equal to V by lambda 1, or nu1 will be equal to V by 4L, as lambda 1 is equal to 4L. This is called the fundamental frequency or pitch of the tone or the first harmonic. Let's move to second mode of vibration. Obviously for n equal to 2, corresponding to n equal to 2, we get the second mode of vibration. So if we consider lambda 2 to be the wavelength of the stationary wave setup corresponding to n equal to 2, then we get L equal to 3 lambda 2 by 4, or from here we get lambda 2 equal to 4L by 3. Therefore, in the second mode of vibration, as L is equal to 3 lambda 2 by 4, the length of the pipe will be equal to 3/4 of the wavelength. So in this manner, as you can see in the picture, the wave will be set up. So obviously, if nu2 is the frequency of the wave setup, then we may write down nu2 to be equal to V by lambda 2, and that is further equal to V by 4L by 3, as lambda 2 is equal to 4L by 3. Solving, we get V nu2 equal to 3B by 4L, and this is equal to thrice of nu1. This means the first overtone is 3 times the fundamental frequency. The first overtone is of thrice the fundamental frequency, and hence we may call it as the third harmonic. Let's discuss third mode of vibration for n equal to 3. In a similar manner, if lambda 3 is the wavelength of the wave setup corresponding to n equal to 3, we get L equal to 5 lambda 3 by 4, or lambda 3 is equal to 4L by 5. Further solving, we get the expression for the frequency nu3 to be equal to 5V by 4L, which is 5 times the fundamental frequency. So we may refer to it as the second overtone or the fifth harmonic. This means in a closed pipe, it always produces odd harmonics, isn't it? Like this is the first harmonic, this is the third harmonic, and this is the fifth harmonic. This means the even harmonics are absent in the closed pipes. So a closed pipe produces odd harmonics only. The manner in which waves will be formed in case of n equal to 3 will be somewhat like this. This is the second overtone or the fifth harmonic, and we must remember once again that a closed pipe produces odd harmonics only. The even harmonics are absent in a closed pipe. In a closed pipe, at the closed end there must always be a node, and at the open end an antinode. So let us generalize. So frequency of the nth mode of vibration will be nu n equal to 2n minus 1 times V by 4L, or we may call it as 2n minus 1 times nu1. So it is the n minus 1th overtone, or 2n minus 1th harmonic. So this shall be how we can analytically study the formation of standing waves in a pipe closed at one end. In our next lesson, we shall be studying the formation of standing waves in a pipe open at both the ends.